Hello, so we're gonna go over just the reduced eye model stuff real quick. Hopefully how I explain it makes sense. If it doesn't, I'm really sorry. I can try explaining it a different way. But we're gonna go over emmetropia, which is just like the normal eye and what it looks like and what all these mean. Myopia and then hyperopia as well. So with emmetropia, forgot to write one thing up here. Or I guess let's back up. One thing to make note of the reduced eye model, or a couple things, is that this front surface power, or I guess the power of the cornea, that's just they just reduced it to take into factor all of the refractive components of the eye. So the lens, the aqueous humor, the vitreous humor, and all that jazz, and just simplified it down to be plus 60, rather than what we learned the surface power of the cornea to be as 48.3. So that's why it's 60. And then they just simplified the index of refraction for the inside as 1.333. And I've noticed that when I do the math for any of the problems with this, that using all 1.333, so not just 1.3, using all of it is important when you're doing the math, just because we're working in millimeters as well. If you don't include that last 3, it can sometimes throw off your calculations. So for emmetropia, what we're looking at here is the secondary focal length. This guy right here. Oh, that's kind of okay. This is the secondary focal length of the front surface power. Okay. And so that secondary focal length matches the axial length of the eye. And so if we were to do the math, which we're going to talk about in a sec, to figure out what correction this emmetropic eye would need in order to have the focal point of this up here to be the same as the axial length, we would find that we would need 0 diopters of correction, right? So, and then if we go down here to myopia, we notice that the secondary focal length of the front surface power is different than the axial length. And so the axial length is too long. And so we need to find some sort of lens to correct for that in order for this focal length to actually be here. And so how we do that, and then this example here is sort of taken straight from the slides. So if you want to look back at his slides and see how he works through it, you can. But basically how we'll do that is, we already know that for 60 diopters, the focal length is this. And so I'm going to go ahead and figure out, okay, what power does it actually need for its axial length? And so what I'm going to do for that is, I'll do an orange. I'll do 1.333, because we're inside the eye at this point, divided by 0.02835 in meters. 1.33, oh my goodness, 1.33 divided by 0.02835. And so that will give us a positive 47.0194 diopters. So that's what the eyeball, the axial length, requires the power to be in order for that focal point to actually be on the retina. So basically we need to find a lens that corrects that positive 60 and makes it a 47.0194. Or we could do a contact lens, right? So I'm going to erase this real quick. So all I need to do here is minus the power that the axial length is. So I'm going to minus, oh my goodness. I'm going to minus, do this, subtracted by 60. And so I'll do a positive 47.0194 diopters minus a positive 60. I think, right? Yeah, 60 diopters. And let's see if I can do the math. And that's going to give us a negative 12.98059. Oh goodness, we'll do 6 right here actually, diopters. So that's the correction that the eye needs right here, like a contact lens, in order to make this 60 turn into this, because the positive 47.0194 diopters is what the eye needs because of how long it is. So, and if you're worried about the signs, just think about, if right now the eye, it almost looks like the focal length is over converged. And so we're going to use a diverging lens to actually push it further away. So we're diverging that light out, okay? So that's how that works. So that's like if you were to use a contact lens. Hopefully that makes sense. And if you wanted to find out where the far point is, basically what the far point is where, simplified, how I think of it is for myopia, where do we need to hold our object so that naturally the light focuses on here. And basically all you need to do is do 1 divided by negative 12.9806. 1 divided by that, and you'll get a negative 0.077 meters. And so that's like right here. And so you can either put on contact lenses to make it clear, or you can hold your object right here and the image will then turn out to be right there. So that's basically what the far point, what it says in the book, I'll just read the definition real quick, is the far point is conjugate with the retina. So the image is focused on the retina. That doesn't make sense to me. So anyways, basically I just think of it, where do I need to hold the object so that the light focuses on the retina? The part where it gets tricky is with hyperopia. So what we see here is that we have our secondary focal length for that 60 diopter front surface for an axial hyperope. So this infers that they're a sphere for the front of their eye. But your axial length for their eye is shorter than that, so it's a plus 19.22. And so we need to find a lens or some type of correction that makes it so that this goes there. So it ends up being here. And we know from our other labs that, or I guess from optics, that if you're hyperope, you need a convex lens. You need a positive power lens. And so that will just converge light more, so it's right here. So let's do the math to figure out what type of correction this eye needs. So we already know that 22.22 millimeters is the secondary focal length of the positive 60, so I'm not going to worry about the math there. But I'm going to go ahead and do the math for the axial length and what the eye needs. And so the eye, according to its axial length, needs a 1.333. Sorry, I forgot to carry that down from the other pictures. Don't forget that last 3 divided by 19, oh my goodness, 0.01922. And that's going to equal, put that in my calculator, 1.333 divided by 0.01922. And I just made these numbers up for the second one. This is in the slides. So the eye, for the axial length, it wants a plus 69.355, I'll do that for now, diopters in order to get the light to focus there. So I'm going to find the difference between those two, and I'm going to write this out below. This has helped me. I'm going to minus the axial length vergence, axial vergence, yada yada, that I found. This isn't textbook, but this is how I remember it. I'm going to minus that by the emmetrope vergence, which is plus 60. Oh, my handwriting, geez. So I'll take let's move this up here out of the way. I'm going to do plus 69.35. I'm going to write it out a little bit more. 4, 8 through 4 minus a positive 60. And that's just going to give us a positive 9.3548. So, if we just do our math, and that applies to the one above, if we do the axial vergence, what it needs, minus by the front surface power of 60, that will give us the correct sign of whether it's converging or diverging lens. And so this one's going to be a positive, a convex lens, a positive 9.3548. So that's what it needs. If we were to find the focal point, the far point for this, I would do a 1 divided by that, and it's going to give me a 0.1098, blah, 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 big number, and that's going to end up having a far point way out here somewhere. So rather than the far point being in front, like a myope is, now it's back there. So that's what that means. This is useful. The far point is really useful information when we're trying to figure out what the spectacle or the glasses prescription will be compared to a contact lens prescription, because there is a 12, based off of what Dr. Pratt uses, there's a 12 millimeter distance between your cornea or your eye and where your glasses sit in front. So let's try those down here real quick. So I'm going to draw our glasses real quick. There's our glasses. They're super cool. And let's just say let's use pink, 12 millimeters from the eye. And earlier we found that the far point was 0.077 meters from the eye. And so I'm just going to draw that in as well. Let's say it's from here to here. That's going to be 0.077 meters. So, and then, we also found that the contact lens, or the power that the eyes need, is right here. Okay, so 12.9806. And I'll write that down here as well. So that's if it's a contact lens prescription. 12.9806. So if we're wearing glasses, though, what prescription do we need? So this question now is very similar to what we've practiced before, where he asks questions like, what light passes through a 12 or 15 diopter converging lens. What is the vergence 3 centimeters from the eye? And so this is kind of similar. We're trying to figure out, okay, the vergence from here to here is 12.9006. What is the vergence 12 millimeters from that? Okay, so it's kind of the same vibe. Hopefully that makes sense. So what I'm going to do is I'm just going to minus this distance from the total distance, and that's going to give me the distance from here to here. Okay, so I'll do 0.077 minus a 0.012, because I want to put it in meters, and that will give us a distance from here to here of 0.065. Okay. Then to find the power that the glasses will need to be at that point, it'll be 1 divided by 0.065, which we will then find that the glasses need to be 15.3846 diopters. And so that's kind of, I don't know, that's a pretty big difference between 12 and 15. And so for a high, this is supposed to be minus. Brain fart. Anyways, so that is pretty substantial between contact lens and glasses lens prescription. From what I understand, I might be wrong, but the higher the power, the more relevant that is. And so if you got a lower power, I don't know if that's as relevant, the difference between the two, but looking from this, it actually looks a little bit more relevant. So let's now do it with a hyperopic eye. So we got someone who's hyperopia. I'm going to look at our math that we did up here. We found that the far point was, I got to do the math again. 1 divided by 1 divided by 9.3548. And so we found the far point for this is going to be way back here somewhere. I'm just going to write down here, far point FP equals 0.106897 meters. And we found that that it needed a plus 93548. So it needed a plus 9.3548. So if we have glasses on the right on here and they're 12 millimeters there, so if that's 12 meters from the cornea, so what's the difference between the divergence right here that we needed for contact lens and the divergence right here that we'll need for glasses? So we'll have to measure from the focal point. So now that the far point. Now that the far point is back here though, we'll have to do our math a little bit differently. So, or do we? No, yeah. So we'll do, before we minus the 12 millimeters from the far point, minus that from this. And now what we're going to do is I'm going to take the far point, which was a positive 0.0109897. Oopsies. 0. that. And it's actually going to get further from that focal point. So it's going to get 12 millimeters further from here. So we're starting at 0.1098, and then we're going to end up being 12 millimeters further from there. So I'm going to add 0.012 plus 0.012, and that's going to give us a distance of 0.118897. And then to find the power of the glasses, we'll do 1 divided by 1. I'm just going to bring over what we just found. And so the glasses will have to be a plus 8.41 diopters-ish. So hopefully that helps describe the difference between, when we use a contact lens versus glasses, and how to use the far point to find the prescription of the glasses. One thing that I want to show and make sure we understand is, why is the prescription less for a hyperope from contact lens to glasses, and why is it more for a myope from contact lens to glasses? And it all has to do with how much closer or further are we getting from that far point. So for a myope, here's the far point. For contact lens, it's further. And then as we get closer, we're getting closer to that far point, the divergence increase. So this goes back to what we learned really early in the semester. The closer we are to a point source or a focal point, the higher the divergence will be. And for hyperope, we see here, the far point is here, and we're starting at the contact lens surface or whatever, the front surface of the eye, and we get further from it. And so that shows the further we are from a point source or a focal point, the lower the divergence will be. So that explains why we see this type of thing with hyperopes and myopes. So anyways, hopefully that helps explain it. Sorry it's a long-winded video. It was one take. All my other ones take me like 5 takes, so yippee. Anyways, thanks.